Computers have a few functionalities programmers typically would not consciously use, but for the sake of optimization, they sometimes should. One such functionality is the Nintendo 64's cache instruction. If programmers don't use it on purpose, compilers never insert this instruction into a program, and to my knowledge, no N64 game uses this instruction outside of some basic hardware communication. You don't need this instruction to program anything at all, and in fact, I imagine many programmers don't even know something like this exists. Manual cache management is out of the realms of what most programmers normally do. But what if I told you, you can double your program's execution speed with just one trick under certain conditions? And it's all because the people designing the Nintendo 64 made one genius decision. They implemented the cache instruction with the create dirty exclusive mode. I'll explain exactly what this does, but first I'll need to explain a bunch of other stuff. I do feel sad for the guys that made the Nintendo 64 hardware because of how underappreciated this effort of theirs went. If developers had taken advantage of this, the Nintendo 64 would not have gotten nearly as bad of a reputation for its slow memory, and that's a tragedy considering virtually every official Nintendo 64 game was bottlenecked by the memory speed. But today, we'll make a bunch of old people that worked at SGI in the 90s very happy by talking about what they've allowed developers to do. Before we get into it, I have to explain the basics of how the cache works and how it is supposed to work. I'll explain it with an easy to understand analogy that accurately represents exactly how cache works on the N64. Even if you do already understand cache, just let me explain this for a bit so I can be free to explain the rest of the video in terms of my analogy. Imagine a city. Let's call this the City of Planning Undertakings, or CPU for short. This city has a cache district with a bus station that drives to random access memory land, or RAM for short. Now, CPU is full of mathematicians. They love numbers so much, but they have no memory at all, so they're unable to store their beloved numbers anywhere. Their memory is so bad actually that even almost all of their math formulas and laws are stored in RAM land. And they can store about 4096 instructions related to their laws and formulas and 8192 numbers in the cache district. These storages are called instruction cache and data cache. But RAMland is different. They have no mathematicians over there, but they've got tons of guys that just love to memorize numbers. So CPU City uses a bus to send letters to and receive letters from RAMland. We call this bus the RAM bus. These letters contain numbers that RAMland can receive and remember for them. Now, running the RAM bus is slow, so this city is trying to not rely on it too much. They don't want the bus to drive unnecessarily, so they only ever call it when they need to. That's why they only ever call the RAM bus to send off numbers to RAMland if the cache district overflows. So when does that overflow happen? This is a bit more complicated. In the cache district, there are just buckets. For the data cache, we have 512 buckets with 16 numbers each in them. The first 16 numbers in RAMland will be put in the first bucket in cache, the next in the second, and so on, until we reach the 513th set of numbers, which will be placed in the first bucket again. The 514th set will go in the second bucket again, and this pattern continues all the way till the end of RAMland. Whenever we're trying to fill a bucket that's already filled, we'll have to empty the previous one first by sending the RAM bus on a journey to store the numbers into RAMland. That way, no change we do in the cache district is ever going to be lost. And whenever the CPU City needs to know a number, they can check if the corresponding cache bucket has a copy of that number and save a RAM bus strip. Great! This lets CPU City operate somewhat efficiently. But that's not all. There's also the issue that only a single RAM bus exists in the world, and CPU is not the only city that wants to know these numbers. The Republic of Computing Polygons, or RCP, would love to know about some of these numbers too. So really, ideally CPU wouldn't use the RAM bus at all, so we don't slow everyone else down by taking control of the RAM bus. Usually, the bus station does a job of managing its trips reasonably well, automatically, without needing any further instruction. Most programs don't consciously do any cache-related instruction stuff at all and just let the bus station do its thing. The bus typically takes multiple thousands of trips in the single frame. But There are a few risks here. What if the RCP writes to RAMland and now the numbers in the CPU cache bucket are outdated? Is the bus station really doing a good job automatically managing its trips? Can we maybe even use the RAM bus or the cache district to do some things that it wasn't designed to do, some dark programming magic? That's where the cache instruction comes into play. And lets us update some information in the cache district to be more efficient and avoid scenarios where our values in cache don't match our values in memory or vice versa. This will be required for loading data from cartridge to memory and to send data off to other hardware parts. Usually, computer processors are designed to a specific standard. The N64 is designed to the MIPS-free standard, which lets hardware designers use a little bit of wiggle room with optional implementations and sometimes even entirely undefined implementations. And the Nintendo 64 had a unique implementation in its cache instruction that lets developers gain an absolutely incredible amount of performance. Shoutouts to Marathon Man for bringing this to my attention. He's the dev of N64, which is one of the most accurate Nintendo 64 emulators ever. The cache instruction has a bunch of different modes that update the information in the cache district in distinct ways. We'll need to go over all the basic ones first, and then we can talk about how Create Dirty Exclusive changes everything and allows us to improve performance. We can't really use this one for optimization, but this is a necessary mode to make the whole system work. Index Invalidate can mark any individual bucket invalid so that the next time we want to read it, we need to fill it again first. We need to run Index Invalidate on all the indices before loading screens, because the loading screens will cause a bunch of data all over the place to change in RAM land via loads from ROM, leading the cache to be completely out of sync with the RAM. The writeback part of Index Invalidate Writeback ensures that any of the changes in our cache buckets get the changes carried over to RAM land before being invalidated. The next mode is Index Load Tag, and already we can do a few very sus things. This one lets us read a cache buckets tag, which contains info about which RAM address a bucket belongs to, whether it's valid, and whether it's been modified since we first loaded it. Since my game has all the graphic and all the sound codes separately, small enough to fit into the 512 instruction cache buckets, we can read a cache buckets tag to find an exact history of what the game was doing a couple of nanoseconds or microseconds ago. And this history could be used to predict which thread will run next while the CPU is waiting for the GPU to finish doing its thing, so we can prepare for a faster startup on the CPU by a couple microseconds, if we guess right. Unfortunately, doing the preparations itself is not free, since it would mean using the RAM bus, so this is actually not that great. I'm currently not using this yet, but even with all those downside, I still believe that this could lead to a very small performance benefit. Of course, we could also load data cache tags, but it's much less reliable since data is referenced across multiple threads, in my game at least. This mode here is actually not even required to be MIPS-free compliant, and that checks out because this instruction borders on useless. Next is Index Store Tag. This one manipulates the tag mentioned previously, and we can use this for really fast memcopy operations. Think about this. We can load a value from RAM at some place and do absolutely nothing with it. We don't care about this value, we just want the bucket to get filled. Then we edit the cache tag of this bucket to be dirty and belonging to the RAM address we want to copy to. And now we just wait. Now, unfortunately, cache tags only contain part of the RAM address they belong to. After all 512 buckets already can only belong to so many possible addresses. That means we can only memcopy data if it's exactly 0x2000 bytes apart, and we can only copy multiples of 16 bytes at a time. Which, if you couldn't tell, is severely limiting, but still theoretically has a use case. This, of course, requires writing back data to memory, which only works in decache mode, is what any reasonable person would think. But you can actually do this with the instruction cache too, for some funny reason. I have no idea why. This console can write back from the instruction cache, which lets us memcopy multiples of 32 bytes in just 5 cycles per line of cache. That's the fastest way to copy data for sure. Unfortunately, I am micromanaging the instruction cache harder than Jeff Bezos micromanages his employees' piss breaks, and using the instruction cache to copy data like this will always result in kicking out data from iCache that is 100% guaranteed to be useful useful again in most situations. I could find one singular use case for this in my entire codebase. Unfortunately, it breaks most emulators because emulators just cannot handle this level of hardware abuse. This is tragic because I absolutely would love to get the most performance out of my game. Also consider that back during the N64's lifetime, they were for sure not making their games for the emulators, which means that if a game can run on an emulator, it just wasn't optimized to this degree. Which is fair enough because I don't think that even the moon landing rockets in 1969 had to run on hardware that was optimized to this degree where cache micromanagement like this was required. Our next operation is hit invalidate. It sounds very similar to index invalidate, but there are two important differences. Hit invalidate lets us invalidate a memory address instead of a cache bucket. Think of it as if the cache bucket associated with this RAM address is being used for this RAM address right now, do an index invalidate operation. This lets us do self-modifying code correctly by just invalidating the modified cached code. It also does not write back the cache to RAM at all, so the changes in cache that are not committed to RAM yet are completely lost. Sounds like it just breaks stuff, but this will be a very useful property later on. The next mode, iCache fill, lets us prefetch memory into cache. This rarely makes sense on the N64 unfortunately, because prefetching cache directly adds lag to any possible process we could be waiting on, unless we are explicitly bottlenecked by a process that does not have memory throughput as its bottleneck. This could, for example, be for RSP bottlenecked tasks. My game is so optimized that the CPU is idle for over 75% of its runtime. Being idle really just means that it's running a permanent infinite loop that does nothing on an idle thread. We could run the iCache fill command in the idle thread to prefetch data for whichever thread we predict to run next. This would allow us to skip a few microseconds of instruction or data loading time, but considering the RSP is still bottlenecked, making the CPU run faster should not really make the RSP any faster. But I don't know, maybe it will. Honestly, it's hard to tell when it's about such small numbers and such an interconnected architecture. There's also a risk of mispredicting the next thread to run and clogging the memory pipeline for no reason, so I guess only attempt can really tell. Another one is hit write back invalidate. Literally the exact same as hit invalidate, except this also writes data back and can only be used on the data cache. This has to be used when we load data from ROM to a RAM address that is not cache line aligned. Imagine a scenario where we modify data in cache and then load from ROM to RAM halfway overlapping our cache line. This will lead to the loaded data not being there in our cached copy, and if we just invalidate, it would lead to our modified data in cache not being written back to RAM. Either way, we need both the write back and also an invalidate. Next up, hit write back. We can use this to flush cache back into memory whenever we send tasks to the RCP. I do this to flush out lights at the same time for my dynamic player lighting, for example. If you are an absolute pro, you can also use this on data cache instead of index write back to reduce the amount of memory transactions when flushing data and getting it ready for the RCP. Let me explain. With index write back invalidate, we will have to go over all 512 buckets and invalidate and write back every single one of them. That costs a lot of memory transfers. With hit write back, we can go over the last 512 RAM addresses that may be associated with our buckets that need to be flushed out. Realistically, not all of them will be, possibly only a handful. In the best case, this would prevent 512 entire memory transactions, which could save as much as 50 microseconds. In the worst case, this is the same cost as index and validate write back. Of course, this is only possible if we can narrow down what the last 512 buckets could be to a reasonably small section of memory to run this command over. I have not implemented this yet because I just now realized the potential while writing the script. I'm excited to give this a try though. I don't think any existing N64 games do this because of how completely unreasonable micromanaging your cache to this degree is, and how the game will just crash instantly if you do it wrong. That is way more risk than most commercial games are willing to take on. A fetch and lock is a recommended operation in MIPS 3 as a 7th operation. But the lock bit doesn't actually exist on the N64, so this is clearly not implemented. However, I am unsure what actually happens when you use the cache operation with operation 7. Someone should look into that. It probably just runs operation 0 or something. And most importantly, create dirty exclusive. This instruction here is not part of the MIPS3 standard, but it is by far the most useful one, and I'm really glad it was added. This is where most of the magic happens, because there is a big issue with the cache setup. You may have noticed that our cache buckets are always 16 bytes big, and the RAM bus is fully filled with the bucket. So, when you want to store something to memory, the console will first store it in a cache bucket. And since a cache bucket has 16 numbers, the console has to fill in the other 15 numbers in the cache bucket first, so that the full cache line matches memory. That means storing a single byte of data causes 16 bytes of data to be loaded. That is obviously terrible. There's nothing we can blanket do to fix this. We can mitigate this by using uncached writes that bypass the cache distance entirely, but that comes with a whole other set of problems. But the create dirty exclusive instruction comes in clutch here. This instruction tells the cache district, don't worry about Ramlan's numbers, your numbers are the real ones now. This essentially picks a random cache bucket and tells it that it now holds the truth about whatever numbers are in RAM. This will usually result in your RAM filling with entirely random garbage numbers that belong to some other spot in memory. But if you're going to write all the 16 bytes of data anyway, this does not matter because you will overwrite the entire contents. That way, we can prevent one entire trip, half the cost of the RAM bus when storing data. And this is useful for stuff where we have to write a lot of data, like a graphics rendering task or an audio rendering task. Applying this optimization all over my codebase saved around 260 microseconds. That does not sound like much, but when you consider that my CPU finishes in about 9 milliseconds, that's a 3% improvement. Very, very nice. Having to load an entire cache line, even though you will overwrite all of it, continues to be an issue on modern hardware. And I'm not sure if anyone is actually actively working around this, or if working around this is even reasonable with how much more contrived cache architecture has become since the Nintendo 64. It might not even be relevant anymore. Modern hardware is much faster. The CPU I'm using to record this video here is about 1,000 times faster than the Nintendo 64, and games nowadays are still below 60 FPS. But whether this has anything to do with memory throughput or not is honestly just not my area of expertise. Maybe someone in comment knows. Either way, on the Nintendo 64, this is an insanely useful trick that would have changed everything had devs known about it. Create dirty exclusive is cool enough as is, but even cooler, it lets us use the other instructions in even better ways. With hit and validate, we can now also use quantum data. Alright, full disclosure, I am not using quantum physics in my Mario 64 mod yet, but the concept is similar. We can leave memory in two useful states at once for two kinds of useful mechanics. In operating system level functions, instead of a stack, we can simply mark a couple of cache lines dirty and valid and overwrite those. And then we can avoid writing those back to RAM using hit and validate. This will let us run all the operating system functions without ever accessing RAM at all. We use the cache memory. Here's how. Instead of allocating stack space at the very beginning, we just mark a couple of cache lines valid and dirty. Then, instead of writing data to a stack, we just write it to some stupid invalid address corresponding to our marked cache lines that may not even exist at all, and pretend like it exists to trick the hardware into letting us use the cache buckets. And then at the end of the function, instead of incrementing or decrementing the stack, we simply hit invalidate to undo our changes to RAM and avoid writing any memory. This way, we've managed to store temporary data without ever having written to memory and without having to pay any memory bus usage penalty at all. The RAM bus doesn't even go vroom anymore. It is straight up retired. This will actually somewhat work on some emulators too, and I plan to take great advantage of this in my OS level functions, since those are such small and controlled environment that this is perfectly reasonable and possible. Similarly, and this one won't work on emulators, we can use hit and validate to put data into a limbo where the console believes it has to write data out to RAM, and then afterwards we can decide whether we want to commit it to RAM or not. Kind of like a superposition between two different valid RAM states that we can decide in post whether we like it. For this one, I don't have a use case right now, but the potential here is huge in my opinion, and maybe I will find the use case one day. So what's the conclusion? It's very commonly stated that the memory throughput is the main bottleneck on the N64, and these tricks can more than double your memory throughput in the best case scenario, which if memory was still the bottleneck at that point, would double the frame rate. Of course, that's unrealistic, as you do need to read some data at the very least. I'd say a 5 to 20% improvement in frame rate across the board is realistic with this trick alone, and that's about what I saw in my game. At least until my game was so optimized that the RSP became the new bottleneck. That makes this game, to the best of my knowledge, the first N64 game to be bottlenecked by the RSP instead of memory bottlenecked. Except for maybe Diddy Kong Racing, which is RSP bottlenecked, but for all the wrong reasons. Shoutouts to Fasana for telling me that. They've been complaining about Diddy Kong Racing's microcode for literal years now. Maybe one day I'll make a video about Diddy Kong Racing with them. All of the performance benefits of these cache modes, instead of Create Dirty exclusive, are oddly specific or incredibly volatile tools for optimization to the point where they're practically unviable to use for most game studios. If I was a plumber and optimization was plumbing, then this video here would be me showcasing my high precision glass wrench and my L385 Hypershitter Model B revision to a 1988 screw for the toilet bowl. You probably won't need these tools on your average job site, correct me if I'm wrong. Shoutouts to all my Patreons for supporting my videos. This video here was available early on Patreon for beta test watching. I won't put any of my mods behind the paywall, not even for early access, but Patrons get early access to videos and any additional questions are being answered. Thanks for the support. I'm also using all of this N64 tech knowledge to make my own N64 game called Return to Yoshi's Island. I've already finished 14 and a half of the 15 courses that are planned in this game, and then it's just beta testing, side levels, and some overworld stuff. Look forward to that. Until then, bye!